Welcome to the fifth. Actually, sorry, this is the sixth online tutorial. Yeah, sorry for mistake on the first slide itself. Uh, yeah, just a second. Yeah, okay. Welcome to our sixth online tutorial session of the NPTEL called Physical and Electrochemical Characterization in Electrochemical Engineering. As you all know, for the past 5 weeks, we have been leading these online tutorial sessions where we actually discuss some more topics, like for some further questions that could have been asked from the lectures that are taught by Professor Tamal Banerjee on his lectures. So we'll be discussing some more questions that I'll be preparing by myself, or I'll be getting those questions from somewhere else. So we'll be discussing that. So I hope these questions has helped you to solve some of the questions in your tutorial sessions or your quizzes or assignments. So yeah, so once again, welcome to the class. So this is the online tutorial session of the physical and electrochemical characterization in chemical engineering. So this is an NPTEL course offered by Professor Tamal Banerjee of Department of IIT Guwahati. So, so in this, we'll be dealing with many characterization techniques that are generally used by, as I always say, these are not just techniques used by chemical engineers, but these techniques are widely used by other branches of sciences like physics, people from physics, usually people who deal with energy materials, or you basically deal with the material synthesis, or the people from the background of material science, nanotechnology, electrochemistry, chemical engineering, maybe people from biotechnology. All these people use these kinds of technique on a day-to-day basis. So these are very fundamental characterization techniques that are very must for any student who is getting into research. So this would be a very efficient and very productive classes for you. So kindly try to attend all the lectures and solve all the assignment questions and tutorials, and try to attend this online tutorial session. So you will be able to get a more clear picture on what is actually taught in the main lecture. So without further ado, let's move on to the next. Let's start the class. So let me introduce myself. I'm Rahul R. I'm a Prime Minister's Research Fellow from the Department of Physics, IIT Kharagpur. So I have been handling this session for last 5 weeks, and I'll be handling this online tutorial for next 2 weeks more. So this is an 8-week course. So we are on our 6th week, and we have um, 2 more weeks to go. And the last class, I hope you remember, we discussed about surface area measurements for using BET. So we have discussed the theory about BET and all those things. So today in this lecture, uh, which is based on the lecture 6th week lecture of Professor Tamal Banerjee, that is actually based on the rheology. So rheology is a very typical kind of study that people from different backgrounds usually do to study the majorly about the viscosity, how the fluid, how the material, which may be in a liquid or semi-liquid form, how that actually moves. Like what are the um, how can we test about the viscosity of that um, viscosity and many other properties too about that fluid. So without further ado, let's move on to the class. So let us discuss our first question. So yeah, let me stop here for a while. So basically, our class will be in such a manner, like I'll just state you the question and I'll give you a few seconds for you guys to think the answer. So once you think the answer, once you are you are confident that you are knowing the answer, then you can rather tell me, or else I will give you a few seconds so that you guys can prepare by yourself, and then later on I will discuss the answer with you. So in this way, this tutorial session is not just a one-way talk. Rather, it will have an equal participation from you guys also. So so, so as I said, after each question, I will read out the question 2 or 3 times for you. Then I will also give you a few seconds for you guys to think about the answer, depending on the question. If the question is very simple, I'll move on to the answer quickly. But if it's a little bit tough question, I will give you enough time so that you guys can actually think the answer first yourself, and then I will tell you the answer, and I will tell you the reason for why that is the particular answer. Yeah. So I think we can start our lecture. So yeah. Today's first question is define rheology. So as I told you, this week's lecture is mainly based on rheology. So one need to know what is rheology first to begin with the whole lecture series. So the first question of today lecture is what is rheology or define rheology. So I can give you a few seconds for you guys to think. Then I will let you know the answer. Okay. So the question is define rheology. So the question was, what is rheology? Think it for a while. Just think it for a few more seconds, then I'll let you know the answer. Yeah. So basically, rheology is that when dealing with rheology, so rheology is a study of the flow of matter. So yeah, as I told earlier, rheology deals with the flow. So it deals with the flow of matter, which is prime fluid in state, but also there are we also deal with some soft solids and solid under different conditions that corresponds to different kinds of flow, like plastic flow and other kind of flow. So rheology is nothing but a study of flow of matter. Rheology is nothing but is nothing but the study, the study of flow of matter, in particular, in particular fluids. So how does a fluid actually flows? So this is studied under rheology. So how? So in simple terms, rheology is nothing but it's a study of how fluids actually flow. Okay, I hope it is clear to you. So rheology is a study of matter's flow and deformation. In simple words, I can tell you how fluids flow. That's it. Okay. So the question was define rheology, and the answer is rheology is a study of matter's flow and deformation. I hope you guys understood. Now let us go to the next question of today's lecture. So the next question is the two main stress deformation relationships that are attributed to a material are. So basically there are two major stress deformation relationships that people actually use while dealing with these rheology problems. So what are those? There are two basics. They can be multiple, but still there are two very fundamental stress deformation relationships. So what are they? So when material scientists or people who actually do these kinds of machines, they regularly come across some very fundamental stress deformation relationship. What are they? So I can give you a few seconds for you guys to think over. Then I will let you know the answer. Okay, just think it for a while. The question is the two main stress deformation relationship that are attributed to a material are. Yeah, stay there. I can give you a few seconds. Just think over it. Then I will discuss the answer with you. I will review the question once again. The two main stress deformation relationships that are attributed to a material are. Okay, so I think you guys had enough time to think over the answer. So now let me discuss the answer with you. So when people are actually dealing with liquid, they actually deal with viscosity. Okay, people actually deal with viscosity. Viscosity is nothing but the resistance of individual layers of a fluid with respect to each other. So how does, if suppose we have a fluid and suppose consider if I can divide it into different parts, something like this. What is the resistance offered by this layer to this layer? So this interlayer resistance is called the viscosity. So for liquids, the stress deformation relations that people actually deal with while they're dealing with liquids are one is viscosity, which is nothing but stress divided by shear height. We will be dealing with these technical terms in the later slide. Stress is nothing but force per area. Stress. And when people are actually dealing with solids, they actually go for modulus. So modulus is nothing but stress by strain. Stress by strain. So we know different kinds of modulus, things, modulus. Yeah. So you all know that stuff from your childhood exam. Okay. So once again, the two main stress deformation relations that are actually attributed to a material are for liquids, people generally tend to go for viscosity, and for solids, people actually prefer modulus. So viscosity is nothing but stress per shear rate, and for solid, it's nothing but modulus is equal to stress by strain. So I hope you guys understood this one. Now let's move on to the next question, and yeah, I hope it is very clear. And the next question is match the following. So this is a match the following question. So we have on the left side, we have in technical terms, which is shear stress, and its corresponding unit is given as Pascal. And second one is viscosity, and then shear rate, then it's shear percentage. So yeah, and corresponding equations are given on the right side. Yeah, there are multiple four equations and there are four technical terms. So we need to match it one to another. So yeah, the things are shear stress, viscosity, shear rate, shear percentage. So just think it for a while, try to work it out. Then I will show you the answer. Okay, just think it for a while. So we have shear stress, viscosity, shear rate, and shear percentage. And their corresponding equations are provided on the right side. Okay, so kindly try to match those things. Hope you will get the answer. Just take it for a while. To match the following question, and you have the left side, you have shear stress, viscosity, shear rate, and shear percentage, and the corresponding formulas are in the jumbled order on the right side. Try to match it out and try to figure it for a while. Then I will give that. Just try it for a few seconds. I think you had enough time to see the answer for yourself. Now let me discuss the answer with you. So the first one is shear stress. So the formula to calculate shear stress is nothing but shear stress. Just a second. The formula to calculate shear stress is nothing but force by area. Shear stress is given by sigma is equal to F, which is force, divided by A, that is the area. Now the next one is viscosity. Viscosity is nothing but it is a ratio of shear stress by the shear rate. We have already seen that. So viscosity is nothing but this one. And this is shear stress divided by shear rate. And the next one is shear rate. So what is the shear rate? So yeah, you can already see that from the symbol itself. So what is the from the representation of shear rate is nothing but shear rate is equal to gamma by T. Okay, and now obviously the last one is shear percentage is nothing but distance or displacement as a function of time divided by x, the x-axis divided by displacement of y. So that is nothing but the shear percentage. So it is nothing but, yeah, obviously you will know that shear percentage is displacement in the x direction by the y direction. Okay, I hope you guys were able to find out the answer. So the answer as shear stress is nothing but sigma, which is represented as sigma, is equal to force by area. Viscosity, which is represented by the Greek alphabet eta, is nothing but sigma, which is the shear stress, divided by gamma dot, which is nothing but the shear rate. And now the shear rate, which has a unit of second inverse, is nothing but gamma is nothing but the shear by time. So how much? Like it's gamma by time, giving gamma dot, and at last shear percentage, which is basically the percentage, is nothing but changing x with like movement in x as a function of time. So as the time moves, the x direction has to change. And what is that? So that x of t divided by y direction, like the quantity on the y direction, like scale on the y direction, would give you gamma, which is the shear percentage. So I hope you guys understood. So shear stress is sigma is equal to F by 8. Viscosity is eta is equal to sigma by gamma dot. Shear rate gamma dot is equal to gamma by T. And shear percentage is gamma is equal to x of T by Y. Yeah, these are the answer. Let's confirm it once again. 1 to B, 2 to D, 3 to A, and 4 to C. Yeah, so the answers are clear. Now let us move on to the next question. So the next question is compare between viscometer and a rheometer. So yeah, so in the class, sir has already told you the details about viscometers and rheometers. So just think it over a while. Just see if you can remember basic differences or the similarities or in general the comparison between a viscometer and a rheometer. Just think it for a while and then I will share the answer with you. Okay, so just think for a while. What is the comparison between the viscometer and the rheometer? Okay. Yeah. So once again, the question was to compare between viscometer and rheometer. So you have to do a basic comparison between the rheometer and a viscometer. Just think for a few more seconds, then I'll let you know the answer. Okay, so I think you guys had enough time to think about the answer, but let me discuss one thing with you. So yeah, before starting, so this is a typical image of a viscometer. So this is a typical image of a viscometer. So the sources are provided below, and this is a typical rheometer. So yeah, now let us see the comparison. So these are the instrument actually. Yeah, that depends on the company who manufactures, and you can add many add-ons. So in general, this is a viscometer and this is a rheometer. Okay, now so the viscometer can measure viscosity in the range about 0.1 to 10 to the power 3 second inverse. So the range that viscometer can actually measure is comparatively very much smaller than rheometer. You can see from this example. So for a rheometer, I mean for a viscometer, it is from 10 raised to minus 1 to 10 to the power 3. For example, for rheometer, it is in the range. So basically, it is in the range 10 to the power minus 1 to 10 to the power 3. But this is in the range which is so huge, which is from 10 to the power minus 6 to 10 to the power 10 to the power 5. So you can see the range that a viscometer can deal is very smaller when compared to that of a rheometer. The range of what? It is a range of measurement of viscosity. Okay. So as you all know, in the previous slide, we saw that viscosity, yeah, viscosity is a very fundamental parameter that people actually measure. So yeah, the range at which they can measure is very small. So sensitivity of rheometer is much more higher when compared to that of a viscometer. Now, viscometer can offer portability for field or remote testing. A rheometer is usually fixed in the laboratory setting. So when you consider the portability, when portability is your main parameter, then you are supposed to go for viscometer. So there are conditions where people actually take the instrument and go into field and do certain measurements. And people, while in most general cases, when people actually do their study while inside a laboratory, people actually prefer this rheometer because it is much more versatile. And yeah, the portability is one of the major issues. Viscometer is portable, whereas rheometer is not that portable. Now, the viscometer can only measure steady shear velocity. Viscosity, not velocity, sorry, it's viscosity. So viscometer can only measure steady shear viscosity, whereas a rheometer can measure the dynamic viscosity, complex viscosity, storage modulus, loss modulus, many other logical parameters. So a rheometer is much more versatile instrument that can measure a wide variety of things that are not actually capable by a viscometer. So that is a major advantage of rheometer. Even though rheometer may be not that portable, or maybe it's not at all portable, but it can actually measure much more wide spectrum of information. Okay, that is not actually possible by a viscometer. And the fourth difference is viscometer is simple and cheaper than rheometer, but it can only measure viscosity under one flow condition. Yeah, obviously we can have an intuition that viscometer is much more cheaper and a much more simple instrument than a rheometer because it does very comparing to rheometer, the capability of viscometer is much more less. So simple, yeah, and you can see it here that the this can measure the viscosity under one flow condition. Okay, whereas a rheometer is a more versatile, I was telling, it's a more versatile and accurate, but it requires more skill and calibration to operate. So one need to have a proper knowledge on the handling, knowledge for handling a rheometer, but comparatively the viscometer is much more easier to handle. Okay, so I hope this is clear. I will just explain you once again. The basic comparison, we will do a basic comparison between two methods. So there are many more differences also, or similarities also. But these are some of the major things that one should be aware of. So basically, a viscometer can measure its viscosity in the range of 10 to the power minus 1 to 10 to the power 3 centimeters. Whereas a rheometer can measure the viscosity in the range of 10 to the power minus 6 to 10 to the power minus plus 5 centimeters. A viscometer can offer portability in the, and whereas a rheometer is usually fixed in the laboratory setting. A viscometer can actually measure only steady shear velocity, whereas a rheometer can actually measure different rheological parameters like complex viscosity, dynamic viscosity, storage modulus, loss modulus, and etc. A viscometer is comparatively much more simpler and cheaper device when we compare it with rheometer, but it has many demerits like it can only measure viscosity under one flow condition. Whereas rheometer is much more a complex device and people need to have proper training to use a rheometer. And obviously, rheometer is much more versatile and it can give much more accurate and sensitive measurements. Okay, so I hope this is very clear to you. And you can see a typical uh, picture of a viscometer and a rheometer on your left side, I mean your right side. Okay, so this is a typical viscometer, this is a typical viscometer, and this is a typical rheometer. So I hope this is clear to you. So this is a very fundamental question that everyone should know as they have already taken this course. Okay, okay, fine. Now let us move on to the next question. The next question is, what are the information that rheometer can provide about the material properties? Yeah, this is a very interesting question. So what are the typical informations that a rheometer can actually provide about the material? Okay, yeah, think it for a while. I'll read the question once. What are the information that a rheometer can provide about the material properties? Okay, think this for a while. Try to get at least a few information that rheometer actually provides. And then later on, I will discuss the answer with you. Okay? Yeah, try it for a while. Then I will give you the answer. Yeah, I will read the question once again. What are the information that the rheometer can provide about the material properties? Think it for a few more seconds, and I will discuss that with you. Okay, now let us move on. Now let us discuss this answer for this particular question. So the question was, what are the information that a rheometer can provide about the material properties? So the answer is, uh, it gives information like about viscosity, which is defined as a material resistance deformation, and it is proportional to shear stress, shear rate, or shear stress. And viscosity is dependent on both time and temperature. So this time and temperature dependent viscosity can be measured, and also it can measure viscoelasticity. So all these things can actually be measured by a meter. Now, just move on to the next question. So what are different kinds of measurement? Okay, yeah. So there's a slight difference. So yeah. So a rheometer works by correlating basically a remote. So the information is like how far the deformations can be pushed. By providing torque or stress, we can measure the angular displacement, which is nothing but the strain. And by providing angular displacement, we can actually measure the torque. So these are the few measurements that a rheometer can actually. So the last question which I wrote was wrong. I'm sorry for giving providing you. So this is a wrong slide. So actually, yeah. So this is actually a wrong slide. Sorry for the misinterpretation. Yeah. Oh yeah. This this is actually this is wrong, and the answer to this is basically the different kinds of measurements that the rheometer performs are, it gives information about how far the deformation can be taken, and by providing a certain torque, we can measure the angular displacement. By providing torque, we can measure the angular displacement omega, and we can also do the reverse of this. We can provide angular displacement and then measure torque. So either we can give torque and measure angular displacement, or we can um, give a angular displacement and measure torque on the material. So yeah, these are the few measurements that can be performed using a rheometer. And the next question is, in a rheometer, the stress is calculated from dash. Okay, I'll read the question once again. In a rheometer, the stress is calculated from dash. Think this for a while, then I'll discuss the answer. the reometer, the stress is calculated from dash. Just think it for a few more seconds, then I will let you know the answer. I think you guys got. I think you guys got enough time to think over the answer. So the answer to this question is nothing but torque. So that actually the in a reometer, the stress is actually calculated from torque. So I think yeah, this is a very easy question. I hope you are were able to get the answer by yourself. Now let's move on to the next question. It is nothing but yeah, the answer is torque. So the next question is explain the expression of strain. So just explain the expression of a strain. Yeah, that's it. This strain is actually the strain used by rheometers, so think it on that scale. So the question is to explain the expression of a strain, which is generally used to rheometer. So think this for a while, then I'll discuss that. See, I'll read the question once again. Explain the expression for strain. Just think this for a while. What is the expression for strain? This is generally used to rheometers. Yeah, think this for a while. Yeah. So I think you had enough time to discuss, like, think the answer for yourself. Now let me discuss the answer. So the strain is generally expressed in the terms of gamma is equal to C lambda times theta. So here basically gamma is the strain and C lambda is nothing but a strain constant and theta is the angular motor differential. The unit of uh, theta is nothing but radians. And C lambda, it's nothing but a strain constant and is a geometry dependent. So it depends on the geometry of the material that you measure. So what is the answer? Gamma is equal to C lambda theta. Okay, so this is the expression for strain. I hope this is clear to you. Now let's move to the next question. What explain the expression for modulus? So yeah, just try to get the modulus. Then I will discuss this. I think we can discuss the answer now. So the answer is basically G, which is the modulus that here that we are talking about, is nothing but gamma by sigma. So yeah, this is a typical expression that people actually use. So this is the expression that is used for the expression of modulus. Okay, now let's move on to the next question. So the question is, how does shear rate is obtained in a rheometer, and explain its expression. Okay, so the question is, how does shear rate is obtained in a rheometer, and just explain its expression. Okay, first question is, how shear rate is obtained in a rheometer, and then we have to explain the expression corresponding to it. Okay, just think it for a while, then I'll let you know the answer. Okay, so I hope the question is clear to you, and now let's discuss the answer. So, in a generic rheometer, the angular velocity is directly recorded and shear rate is obtained using the formula. So we get the angular velocity, and then using that we get the shear rate, which is nothing but the gamma dot. Yeah, and this is of the relation gamma dot is equal to C lambda omega. So omega is the angular velocity. And this is a strain constant. Okay, so yeah, where gamma dot is a shear rate and C lambda is a strain constant, gamma is the angular velocity, and the unit is radian per second. And yeah, C lambda is a strain constant which is geometrically dependent, that is, it depend on the geometry that we are actually measuring. Now let us move on to the next question. So, what are the different possible arrangements in a room? Yeah. So yeah, the question is, what are the possible arrangements in a rheometer? So in rheometer, there are different kinds of arrangement that are possible. So try to name. So basically, there are four types of arrangement. So if possible, try to name all those things and just try to get a glimpse of what sir has actually taught in the class. So there are actually four types of uh, arrangements that are possible in a rheometer, and try to figure it out. I will discuss the answer with you in a few seconds. Okay. Yeah. Yeah. So I hope you were able to get an idea about the answer. So the question was, what are the different possible arrangements in the rheometer? So the answer to this question is, a rheometer have different geometries depending on the type of fluid and the rheological parameters that has to be measured. Some of the arrangement, the first one is the cone and plate arrangement. Here, a cone with a small angle is placed on top of a flat plate. So something like this is placed on the top of a flat plate, and the fluid is filled in the gap between them. So fluid is filled in the gap between them. So here the fluid is filled. The cone or the plate can be rotated to apply shear stress to the fluid. So either cone is rotated or else the plate is rotated to get a shear strain on shear stress on the fluid. So can be shear stress on the fluid. So either this cone or the plate is rotated so that the fluid experiences shear stress, and then corresponding rheological parameters will be measured. The second one is parallel plate. Here, two flat plates are placed parallel to each other, and the fluid is filled between the gap. The upper and lower plate is rotated or oscillated to apply shear stress to the fluid. So here, what happens is that instead of a cone, here we use two flat plates, and the fluid is filled in between this. So this is the fluid, and then the upper plate or the lower plate is rotated so that the fluid inside will experience shear stress. And from this shear stress, corresponding rheological rheological parameters will be measured. And the next one is a concentric cylinder. A cylinder cup is placed inside another cylinder cup and the fluid is filled in between them. The inner or the outer cup can be rotated to apply shear stress on the fluid. So here what we do is that here we will be having two concentric cylinders, one like this. So similarly, here we are having two cylinders, so concentric to one another. Yeah, just a second. Yeah, concentric to that the fluid is filled in between this. In this gap, people actually the fluid is actually filled, and then in the cylindrical cup or the external is rotated so that this fluid in between them will actually experience a shear stress. And the other one is relative geometries. These are the geometries that do not have any fixed shape, size, such as fingers, main rotors, stirrers, or geometries that is raw serrated surfaces. They use the fluid that are difficult to measure with absolute geometries, such as phased gel or suspensions. So when we have fluids which are usually difficult to measure with regular geometries, then, for example, when we are having certain fluids like paste or gel, which are difficult to be measured in any of the above mentioned techniques, people actually go for relative geometry, where there won't be any particular geometry to this apparatus. So instead, they will go for some random apparatus, and then, and for example, for these are spindles, wheel rotors, stirrers, yeah. So yeah, as I said, there are four different types of arrangements. One is cone plate, the other one is parallel plate, then it's concentric cylinder, then the last one is relative geometries. In cone plate, there will be a cone with a very small angle, and on the side it's a plate, and the fluid is filled in between this space, and then either the cone or the plate is rotated to a certain angle so that the fluid in between observes some shear stress. The next one is parallel plate, where two flat plates are separated by very small distance, and then the fluid is filled in between them, and then either of the plate is rotated so that the fluid will experience a shear stress, and then correspondingly the other rheological parameters will be measured. The other one is concentric cylinder, where two cylindrical cups are placed inside one. Like there will be two cylinders, one is smaller, the other one is larger. And yeah, obviously their diameter is or difference in the diameter is a very small units. maybe in the order of few millimeters. So yeah, and they are separated, and the fluid whose rheological parameters should be measured is filled in between these concentric cylinders, and then either of the cylinder, maybe the outer or maybe the inner, will be rotated for so that the material or inside or in between them would experience some shear stress, and then correspondingly we can measure the rheological parameters. The next uh, arrangement is relative geometries. So for example, if we have certain materials which has a very different kinds of like texture, for example, paste, gel, or some other kind of suspension, which is difficult to measure in any of the above following above stated techniques, people actually go for this relative geometries. For example, in the relative geometry, there won't be fixed shape, size, or anything. For examples, for these are spindles, vein rotors, stirrers, or geometry with rough or serrated surfaces. So people actually go for these kinds of apparatus or arrangements if they have to measure the rheological parameters of paste, gels, or other suspensions. Okay, so I hope this is clear for you. So the four different arrangements are cone plate, parallel plate, concentric cylinder, and relative geometries. So I hope this is clear to you. Now let's move on to the next question. The next question is, in a parallel plate rheometer with decreasing gap height, the dash increases. Okay, in a parallel plate rheometer. So the last question I have already discussed in what is parallel plate. So in a parallel plate rheometer, we'll be having two parallel plates that are separated by very small distance, and the fluid is filled in this gap. So this dash thing is nothing but the fluid. So this is plate 1 and this is plate 2. Now let h be the height difference between, so the gap between these two height. Okay. So the question is, as this h decreases, something increases. Okay, so what is that thing that actually increases when we decrease this distance of separation between the plates? Okay, so think this for a while, and I'll let you know the answer. So in a parallel plate rheometer setup with decreasing gap width, the dash increases. Think it for a while, then I will let you know the answer. Yeah, I think you guys were able to think the answer. So the question was the parallel plate geometry setup with the decreasing gap height, the dash increases. So the answer to this question is shear rate. Yeah. Right. So yeah, as we already thought, the parallel plate, there will be two parallel plates that will be separated by a very small distance, and the fluid will be filled in this gap in between. Now, either of this plate will be rotated, and this is separated by a very small distance h. So, as this h increases, the shear rate that experienced by this fluid will actually increases because, yeah, the force, the impact that of the waste that it receives would also increases as this distance actually decreases. So there will be both a compressive force and it together with the twist would create a larger shear rate when the distance is smaller. So I hope this is clear to you. Now let's move to the next question. Yeah, answer to the question is shear rate. In a parallel plate rheometer setup, the plate gap is in the order of dash. So as I told you in the parallel plate setup, we have two plates and the fluid is filled between, and these plates are separated by a very small distance h. What is the order? What is the order of h? Okay, just think this for a while, then we'll get to the answer. Question is once again the parallel plate rheometer setup. The parallel plate is in the order of dash. Just take it for a while, then I will tell you the answer. Yeah. So the answer to this question is usually this height will be in the order of, as I say, it will be in the order of few millimeters. So the exact answer is it is in the order of 0.52 millimeters. Okay. So In a parallel plate diameter system, the plane gap is in the order of 0.0 actually. Right? So it's actually the rate 0.52 millimeters. I hope the answer is clear to. Now let's move on to the next question. What is effective shear rate? So yeah, now you have a parallel plate. So this is as shown here. So the question is, what is effective shear rate? Did the answer for a while? Then I'll let you know the answer. So the question is, what is effective shear rate? Yeah. So the question was, what is effective shear rate? The answer to this question is, for a given angle of deformation, the arc of deformation is larger than the plate's border, then it's in the middle. So here what it says that the deformation is larger near plate's border than it is in the middle. So we have something like this. The deformation would be larger on the near to the plate surface than on the middle. So this shear rate R is given by effective shear rate, which is a function of H, is given by dx by dh. So effective shear rate tells us that the shear rate will be will not be in a uniform manner, but the shear rate will be larger when in the region which is near to the plate, and it will be smaller as we move towards the center. So at the center, the shear rate will be minimum, and on the border, like at the interface with the plate and the material, and that specific region, the shear rate will be very high than that of in the middle. So yeah, so the answer to this question is, for a given angular deformation, the arc of deformation is larger near the plate's border than in the middle. So this is the shear effective shear rate. Now let's move on to the next question. So this is a match the following question. So here we have a chord plate arrangement. So which is a proper technique for filling? So there are three scenarios where three different kinds of filling is shown. We have to identify which is the fill, which is underfill, and which is the overfill arrangement. Just think this for a while, then I'll let you know the answer. Okay, so now let's discuss the answer. The first one, as we can see, there is no fluid in this region or this region, or say this region or this region. And typically, yeah, obviously we can see that this is a underfilled condition. And this can see like the actually this fluid is coming out so much. So this is a typical overfilling case. And you can see from the figure 2, which is obviously it is the right filling. Okay, so this is underfilled. This is overfilled, and this is right filled. I hope this is clear to you. Now let's move on to the next question. Yeah, already the answer is given here. So the next question is define complex fluid. So yeah, since the answer is already given here, let's not waste the time. So a complex fluid is a mixture that has a coexistence between two phases such as solid liquid or solid gas or liquid gas or liquid liquid. They have unusual mechanical response to the applied stress or strain due to the geometrical constraints of the phase coexistence. Some examples of the complex fluids include polymer solution, liquid crystals, gels, suspension, emulsions, and micellar solution. Okay. Basically, a complex fluid is a mixture of two or more fluids. Like it can be either solid, it can be either solid, like not solid, can be the solid liquid, solid gas, or a liquid gas or liquid liquid. So either in any way, like we have two different phases that are joining. Liquid we meet two different liquids. So two different liquids may have two different parameters, like they have two different viscosities. Or yeah, they can be yeah, there can be two different properties for two liquids. So in that way, basically a complex fluid is a coexistence between two phases, and these complex fluids have a different altogether mechanical response to the applied stress or strain, and that is generally preserved or that is generally observed in conventional fluids. So in complex fluids, these some anomalies or this unusual behavior can be due to the different geometrical constraints that generally occur in the due to this phase coexistence. Some general examples are some liquid crystal, gel, suspension, emulsions, and there's a oil water emulsion, something like that. These are all an example for complex fluid, and the cellular solutions are also an example for this complex fluids. Now let's move on to the next question. The next question is a Newtonian fluid exhibits dash between the applied shear stress and shear rate. Okay. Yeah. The question is the question is a Newtonian fluid Newtonian fluid exhibits a dash between applied shear stress and shear rate. Okay. I hope the question is clear to you. Think this for a while, then I'll discuss the answer with you. Okay. The question was a Newtonian fluid exhibits dash between applied shear stress and shear rate. Okay, so the answer to this question is a linear connection. So the answer is linear connection. Okay, so for a Newtonian fluid, um, the shear stress and shear rate is actually in a linear manner. So if you plot shear stress on the y-axis and shear rate on the x-axis, and then you plot the graph. What you actually observe is a straight line. So it means that shear stress increases linearly with increasing the shear rate. So that is a typical characteristics observed for a Newtonian fluid. So not all the different kinds of fluid will exhibit this kind of a behavior. So only the Newtonian kind of fluids will have a linear connection between shear stress and shear rate. Now the next question is three Newtonian fluid stress components acting on x direction are. So we need a formula. So we need the formula for three. So basically this is a tensor stress components are this stress tensor. So there are three different components for a Newtonian field stress, and that is especially acting on the x direction. And we need to specify the reasons. So these kinds of formulas will be very useful and handy when you actually do some kind of numericals. So just try to remember what those three equations are. Then later I will let you know the answer. Okay. Yeah. Okay. I think you had enough time to think the answer. Now the answer to this question is three stress components are sigma xx is equal to minus 2 eta dou vx by x, sigma xy is equal to minus eta dou vx by dou y plus dou vy by dou x, and sigma xz, the third component is nothing but minus eta dou vx by dou z plus dou vz by dou x. So these are the three stress components that are actually acting for a Newtonian fluid. Now let's move on to the next question. The Newtonian behavior departure occurs when? So when does a material observe a departure from the Newtonian behavior? The Newtonian behavior departure occurs when dash. So think the question for a while, then I'll let you know the answer. Okay. So the question was the Newtonian behavior departure occurs when dash. Think this for a few more seconds, then I'll let you know the answer. Okay, so the answer to this question is the departure from the Newton behavior occurs when a simple shear measurement do not traverse the origin or fail to establish a linear connection between the shear stress and strain. The second one is the apparent viscosity is not constant and it remained by both of these factors. And the substances are variably refers to as viscous, inelastic, time-independent, generalized Newtonian fluids. Okay. So when the shear measurements actually when that do not pressure traverse the origin of traverse the origin or fail to establish a when we actually fail to establish a linear connection between shear stress and shear strain, we can say that the Newtonian behavior is actually departure from the material. So yeah, this is the answer. So let's move to the next question. So what are viscoelastic fluids? Okay, the question is what are viscoelastic fluids? Think this for a while, then I will let you know the answer. So the answer to this question is systems show both. So viscous fluids are fluids, which shows both viscous fluid-like and elastic solid-like behavior. Okay, so viscoelastic fluids generally have the characteristics of both viscous-like fluid and elastic-like solids. So this is a combination of both. For example, family of materials that exhibit incomplete elastic recovery, recoil, and creep among the other properties. So these kinds of materials has these properties like incomplete elastic recovery, recoil, or creep. So these are the basic different viscoelastic fluids. Now let's move on to the next question. So that is, what are the three types of non-Newtonian fluids? Okay. So basically, non-Newtonian fluids can be classified into three different types. So what are they? Just think it for a while, then I will need to do the answer. So what are the three different types of non-Newtonian fluids? Okay, I hope you had enough time to think about the answer. So the answer to this question is the first one is purely viscous, inelastic, and time dependent. Okay. So the three types. So the first type is purely viscous, inelastic, and time. So it actually means that the system where shear rate is determined only through shear stress at that point. That is shear thickening or shear thinning. Okay. The first type is the system where the strain rate is determined only through the shear stress at that point. Okay, so yeah, these are generally purely viscous, inelastic, and time dependent. The next type of Newtonian types of non-Newtonian types of fluids are the time independent fluids, where the relationship between the shear stress and shear rate is governed by the duration of shear, and it is previous kinematic history. That is shear thickening or shear thinning. Okay, so here what happens is that instead of just uh, depending on the shear stress or shear rate at a particular point in time, it actually depends on the duration at which the shear actually been experienced. And it also depends on the previous kinematic history of the material. Okay, so it is not just something that is unproven, but it also depends for a duration. The last one is viscoelastic behavior. It means that it shows a blend of elastic like behavior and a viscous like behavior. So there are materials which shows a blend of elastic like material and viscous like material, and those are called non-Newtonian fluids. So I hope you were able to understand the answer. Now let us not waste this time and let's move on to the next question. That is to identify A, B, C, D, and E. So these graphs actually represents different kinds of fluids. So there is a type A where the stress shear rate, as the shear rate actually increases, the shear stress actually increases drastically. Then at a certain point, it actually goes into a saturated form. And there is another kind of graph which is represented by B, which is a linear as the shear rate vary linearly with respect to shear stress, but it does not actually originate from the origin. Okay. Similar is the case for A. It doesn't actually originate from A, Z origin. Okay, so A, in case of A, we can observe that as the shear rate increases, shear stress increases dramatically at the initial point, then it actually saturates down. And when the shear rate is zero, the shear stress does not goes to zero. So there is a inbuilt shear stress to the material. And the next kind of fluid is where there is a shear stress even at a zero shear rate, and that shear stress would increase linearly when the shear rate is increased. Now, the other kind, which is represented by C, here we can note that the shear rate is actually increasing dramatically in the beginning, just like that of A. Then it saturates, similar to that of A. But when the shear rate is zero, the shear stress is also zero. So the graph actually originates from the origin. Now, on the next graph, which is shown as D, here what happens is that when the shear rate increases, the shear stress also increases in a linear fashion. And when the shear rate is zero, the shear stress is also zero, which means that this particular graph actually originates from zero. And the other type, which is the last type E, is where as the shear rate increases, the shear stress very gradually increases. After a certain point, like it started, no? After a certain point, then as shear rate start increasing, then the shear rate also start increasing dramatically. So in the initial state, the rate at which the shear rate stress increases is very small, and it actually picks up as the shear rate increases to a higher value. And one more thing to note here is that at zero shear rate, the shear stress is also zero. Okay. Now you guys need to identify what kind of fluid is belongs to A, B, C, D, and E. I can give you a few seconds to think the answer. Then I will give you an answer. Okay. Yeah. Think this for a while. We have verified what does A, B, C, D, and E corresponds to. So which corresponding fluid behavior is shown by A, B, C, and C, D, and E. Just give us for a few more seconds, then I will let you know the answer. Okay, now let's discuss the answer. So the first one corresponds to viscoplastic fluid. Okay, so A corresponds to the graph for a viscoplastic fluid. So viscoplastic fluid is a kind of non-Newtonian fluid that exhibit both viscous and elastic behavior, such as stress, relaxation, and elastic recovery. Okay, so the example for a viscoplastic fluid is toothpaste, mayonnaise, etc. Okay. So viscoelastic fluid, here we can see that even though the shear rate is zero, the shear stress is not zero. And in this exhibit both viscous and elastic behavior, such as stress, relaxation, and elastic recovery. The examples are toothpaste, mayonnaise, etc. The B corresponds to Bingham plastic. In Bingham plastic, it is also a viscoplastic material that behaves as a rigid body at low stresses, but it follows a viscous fluid at high stresses. Okay, when a very low stress is provided, it behaves as a rigid body, but when certainly higher uh, certainly higher um, stresses provided, it behaves like a viscous fluid. We can see that even though the shear rate is zero, the shear stress is not equal to zero. And as the shear rate increases, the shear stress also increases linearly. Some examples from Bingham plastics are clay suspensions, drilling mud, etc. Now let's move on to the C. C corresponds to a pseudoplastic fluid. A pseudoplastic fluid is also Gaussian thinning fluid. It's a kind of non-Newtonian fluid that decreases its velocity as the shear rate increases. Okay, so as we can see from this, initially the shear rate, as the shear rate increases, shear stress increases drastically. But after a certain time, it started to reach not it is not actually going to saturate it. It's actually decreasing. Okay, so these kinds of materials are called pseudoplastic fluids. Some examples are polymer solution, blood, ketchup, honey, paint, etc. Okay, now let's move on to the next question. Next graph, which is represented by D, where the shear rate is actually proportional to shear stress, and it actually becomes zero at zero shear rate. And this is an example for Newtonian fluid, and the commonly known things such as air, water are an example for Newtonian fluid. And the last is the dilatant fluid. The dilatant fluid is a non-Newtonian fluid that actually increases its viscosity as the shear rate increases. Okay, so when the shear rate increases, the shear stress also increases drastically, which means that the viscosity actually increases when we increase the shear rate. The example for this is cornstarch and water mixtures, sand and water mixtures, and some clay suspensions. Okay. Yeah, so I hope this is clear. A corresponds to viscoplastic fluid, B corresponds to Bingham plastic, C corresponds to pseudoplastic fluid, D corresponds to Newtonian fluid, E corresponds to dilatant fluid. Okay, I hope this is clear. Now let's move on to the next question. What is uh, thixotropic behavior and rheopathic behavior? Okay, the question is, what is thixotropic behavior and rheopathic behavior? Exotropic behavior and rheopectic behavior. Think this for a while, then I'll let you know. Okay. Now let's discuss the answer. The question was what is thixotropic behavior and rheopectic behavior? So the answer to this question is in a thixotropic fluid is a kind of fluid that becomes less viscous when it is shaken or agitated for a long period of time. So after removing the external shear and allowing the fluid to rest for an extended length of time, the fluid may recover, but the original viscosity will recover its original viscosity. Examples, thixotropic fluids are feed, yogurt, blood, etc. So in a thixotropic fluid, it becomes less viscous. So the viscosity actually lessen when it is shaken or agitated for a long time. So when paint or yogurt or blood, when it's agitated for a long period of time, the viscosity of it will be smaller, and after some time it will regain its original viscosity value. Whereas the rheopectic fluid is that become more viscous when shaken or agitated. Some examples are clay suspension, cream, etc. Okay, yeah. So so thixotropic fluid is nothing but it becomes more viscous when it is shaken or agitated for a long period of time, not for a long period, for a certain period of time. And whereas the rheopectic fluid is the opposite to it, like when it is shaken, it becomes more viscous. Thixo- Thixotropic becomes less viscous after agitation. Rheopectic becomes more viscous after agitation. So that can be observed from the graph as shown here. Mm. So here you can see that as the shear rate for thixotropic fluids, as the shear rate increases, the shear stress also increases, and after certain time, the shear stress drops. And it forms a hysteresis layer. And whereas for rheopectic fluid, the shear rate actually increases very slowly, and after certain shear rate, it increases drastically, which corresponds to higher viscosity value. And then you can see that it also form a hysteresis loop. And yeah, these are the two different kinds of fluid behavior. One is thixotropic and other is rheopectic. I hope this is clear to you. Now let's move on to the next question. That is, what are different viscoelastic parameters? There are different viscoelastic parameters. Viscoelastic, not vasco, I mean viscoelastic parameters. So viscoelastic materials are basically the materials that show both elasticity and viscosity. So it's a combination of both. So what are those parameters? Just think that for a while, then I'll let you know the answer. Yeah, I hope that I will move on to the next question. The answer. The the different kinds of velocity parameters are first one, the modulus, measures the material overall resistance to deformation, which is given by stress by strain. And the next one is elastic modulus, or it is also called the storage modulus. It measures the elasticity of the material, that is the ability of the material to store energy. It is nothing but stress by strain multiplied by a cos delta factor. Now, the next one is a viscous modulus. It's the ability of a material to dissipate energy. The energy is usually lost in the form of heat. It is given by the formula stress by strain into sine delta. And the last one is tan delta, which is a measure of material damping, such as vibration or sound damping. So how much the material can actually damp a vibration or sound is given by tan delta, and the tan delta is given by viscous modulus divided by the storage modulus. Okay, so the ratio between viscous modulus and storage modulus will give us the measure of how cool, the material can damp vibration or sound. Okay, so the different viscoelastic parameters are the modulus, the storage modulus, the loss modulus, and the time delta. I hope this is clear to you. Let's move on to the next question. So the question is, briefly explain the equation of oscillation in rheology. So there is a certain equation that is associated with oscillation in rheology. So what is that? What is that certain equation that that actually defines the oscillation in rheology? I can give you a few seconds for you guys to think over the answer, then I'll discuss the answer. Okay, now let me discuss the answer with you. The equation that is used for the oscillation in rheology is nothing but sigma equal to eta gamma dot. So sigma is the stress and eta is the viscosity and gamma dot is the strain rate. The strain rate can be represented in the form of gamma m omega sine pi by 2 omega t. Yeah, so basically this is the equation. Now I can write eta gamma m as sigma m, and the final the equation is, so yeah, I can write the equation for you. So sigma is nothing but eta gamma dot, where gamma is actually given as some constant gamma m cos pi by 2 plus omega t. So the gamma dot can be found as gamma m, which is a constant, sine pi by 2 plus omega t into pi by 2. So there's actually minus sign. So yeah, just neglect that side. Now it's plus. And this is the answer. Okay. So now substituting this here, I can write sigma is equal to eta gamma m omega sine pi by 2 plus omega t. Clubbing all these constants together to form some gamma m. I can write that multiply sigma m. I can write that sigma is equal to sigma m sine pi by 2 plus omega t. So this is the equation that is generally used to define the oscillations in rheology. I hope this is clear to you. Now let's go on to the next question. Suppose a wheel rotates at a constant speed above 10 revolutions per minute. What are the angular velocity and frequency? Okay. So this is a numerical question. So the question is, suppose a wheel rotates at a constant speed of 10 revolutions per minute. So it's given in terms of RPM. So the RPM of this particular wheel is 10, and what are its angular velocity and frequency. So we just need to calculate what is its angular velocity and its angular frequency. So think this for a while, then I'll discuss that with you. Does not waste the time. So let's move on to the answer. So initially we need to convert. So here in the question it is given in terms of RPM. So the first thing that we have to do is to convert this RPM to radians per second. So we know that there are so one revolution, which is a complete revolution, when it starts from one point and it goes to a 360 rotation and comes back to its original position. It is called a revolution, and it corresponds to 360. As I told you, it's 360 degree and corresponds to 10 radians. So 10 RPM corresponds to 10 into 2 pi radian. So 1 RPM, one rotation corresponds to 2 pi radian rotation. So 10 rotation corresponds to 2 pi into 10 radian. Now 10 rotation per minute per 1 minute can also be written as 10 rotation per 60 seconds. Then it can also be written as 2 pi into 10 by 60 rad per seconds. Can cancel zeros, then cancel 2, so it is nothing but pi by 3 rad per seconds. Okay, radian per second. So this is the angular frequency. Now we can convert. So this is angular frequency. Now to find this angular velocity, I mean, so radian per second is nothing but the velocity. Now we need to find the frequency. For that, we can get this idea like for one revolution is equal to one cycle. So one revolution corresponds to one cycle, and 10 revolution corresponds to 10 number of cycles per minute. Okay, so it is nothing but, so this is one cycle. So 10 RPM or 10 revolutions, in the sense it is in this manner 10 revolution. So this is a 1 RPM, or if we are talking about 1 RPM, it is basically 1 by 10 hertz, 1 by 60 hertz, or where 60 is converting minute to seconds. So it's, and if it's 10 RPM per minute, it is rotating 10 times. So it is basically 10 by 60 second inverse. So it is basically 1 by 6 second inverse. Now we know omega is equal to, we are now just confirming omega is equal to 2 pi f, and we got f to be 1 by 6 second inverse. So we can write this as 2 pi into 1 by 6 second inverse. So cancelling is 2 and 6 to 3. It is nothing but 2 pi by 3 second inverse. So omega is nothing but 2 pi by 3 second inverse. So I hope this is clear to you. This is a very simple numerical that everyone can solve very easily. So I hope this is clear to you. So if it's clear, now let's move on to the next question. Which of the following represent a Hookean solid and a Newtonian solid? So one represents Hookean solid and the other represents a Newtonian solid. Okay, just think this for a while, then I'll discuss the answer with you. Well, I hope you had enough time to think about the answer. So the answer is figure A represents the Hookean solid. This is because the stress and strain plots here has zero phase difference, whereas the figure P corresponds to a Newtonian solid. Here we can see that the stress and strain graphs are separated by a 90-degree phase. Okay, so when there is a 90-degree phase shift between stress and strain, it corresponds to Newtonian solid. And when there is a 0-degree phase shift between stress and strain plots, then it is a Hookean solid. Now, the last question for today's lecture is what are hydrogens? We'll just think it for a while, then we'll discuss that. I hope you had enough time to think. So hydrogens are porous and permeable material, and that means that there is enough water and molecules can pass through them. Hydrogels have many applications in biomedical, environmental, and industrial fields. Some examples for hydrogels are that are used in regular basis are they are used in wound dressings, they are used in the drug delivery system, they are used in tissue engineering, sensors, water purification, etc. So hydrogels are a kind of material that is very porous and very light in their flow. And due to this high porosity, there can be enough flow of water and other molecules through them. I hope this is clear. So that's all for today. I hope everything is clear to you. All these videos will be uploaded in the YouTube channel and links will be shared to you. If you have any doubts, kindly contact me. So I'll be ready to help you at any point of time. And practice these questions once. And yeah, we will see you on the next class. So we will see you on the next week. And we are approaching to the end of these sessions, and I will be here only for just 2 more weeks. And yeah, hope to see you on the next week. Bye bye. Thank you.